Yeah, 5 minutes. Yeah, you tell me. Yeah. Okay. Well, so I guess my talk is slightly different from other speakers. It's more on robotics than on humans. It's about a new take on computing regions of attraction, which is a very important thing for people who are doing legged robotics. So traditional idea of analyzing periodic motion is to think about limit cycles, so something which is periodic. Take a section called a Poincare section. This, you can represent this with a fixed point which characterizes steady state motion. So you find what are the roots of this particular map. You find the stability by taking the Jacobian of this, and the eigenvalues gives you the stability. So the biggest eigenvalue tells you about the stability. If it's greater than 1, the system is unstable and stable otherwise. The issue with this approach is that this expansion, the Jacobian, is valid for small perturbation and only gives you asymptotic stability, which is, in my opinion, it's very slow. So here's a new way of thinking about this. So what we've done is, well, think of a Lyapunov function on the Poincare section. So V is a Lyapunov function, and that is, in this case, just an ellipse, but you could have anything you want. It has the properties of a Lyapunov function, right? It should be positive, definite, and so on. Here, delta x is the difference between the state and the fixed point, which is shown by the star. So V here is in here an ellipse. So one important thing here is we start assuming a region of attraction. We do not compute it later on. So once we have that, we can say that we want to have a fast convergence. So we specify what is known as we specify rate of convergence. So rate of stabilization given by this formula. This is just saying that the state V delta x I plus 1, the next step, should decay in an exponential way. And this is the discrete analog of the continuous time exponential stabilization. So given this, you can sub in the value for, you can write V in terms of F, which is the Poincare map, which relates the state from one step to the next step. And since we can, actually control the U, we can actually control how we can stabilize the system. So this is what I would call a control Lyapunov function, because the Lyapunov function, traditional sense, is just a function of the state, but here it's a function of the state as well as the controls. So this is the only condition we need to satisfy in order to have exponential convergence. So once we have that, what we can do is we use a data-driven approach, which is we take points on the ellipse and put that condition and make a table of states which are around the ellipse, find the controls, and when you think of controls, we're thinking of once per step controls, so foot placement or push off and so on. Once we have this table, we can then think of using regression or, if you like, deep learning, whatever you want, to fit a function which maps the controls U to the system state. So we tried this on a simple hopping model. There are 3 control actions. There's a foot placement theta. There is a braking force. So this is essentially assuming that you can control the force at the leg, and you can put a thrust force. So braking force, thrust force, foot placement. So there are 3 control actions. The hopper is described by 2 states at the Poincare section. One is the apex height, and the other is the horizontal velocity. Given that, we can go through the whole process I described, find control actions which will give exponential stabilization. And this is basically not a table, but showing what are the control actions needed for in this case, decay from V to 0.01 V. So we have an exponential decay of factor of 0.9. What's interesting is that brake force, there's no force needed when the energy is higher. So this line actually is the line of constant energy, so anything above this is going to be high energy, and so you do not need a brake force. Same for thrust force. So we tried different Fs, linear, quadratic, neural network. This is basically taking a bunch of points in the ellipse and finding how the Lyapunov function decays after one step. And you can see that quadratic is better than linear, but if you use a neural network to fit the data, find a control law, it's much better. So in summary, traditional way of doing this is to assume a linear controller and find the biggest region of attraction. The work which is closest to this is Russ Frederick's work. What we try to do here is assume a region of attraction and then find a nonlinear control law. So what this does is it gives a bigger region of attraction, but clearly it's data driven, it's more computationally intensive. We are building a hopper. Hopefully we'll have results next year at Dynamic Walking, but I didn't want to disappoint you, so I actually have results, prototype results. You'll be amazed by not only the Leggett system, but also by the boom which we created. Ready for this?
Who's your co-author on this class?
My kids. Okay, so questions?
Hi, over here.
Yeah.
So how do you find these Lyapunov functions? If you just assume them in advance, where do they come from?
So I start off assuming Lyapunov function. The traditional idea is to, I think the fact that you compute the Lyapunov function in traditional sense is because you assume a linear control that imposes a constraint that the Lyapunov function can only be, well, if you say you want to find the biggest Lyapunov function, then that constrains you. What I'm saying is, let's start assuming a Lyapunov function. When I say Lyapunov, it's actually a control Lyapunov function. So you can control the controls, which will enable that you get that region of attraction. So it's sort of a different way of getting Lyapunov function. So I do not compute Lyapunov function. I just assume them, and I get a control law which will satisfy that particular Lyapunov function. Does that answer your question?
Yeah, somewhat. We'll talk later, maybe.
Oh, you can keep, if you want to clarify, go for it.
Well, then I guess I imagine that if you're, for example, for a quadratic Lyapunov function, you're just changing the Q matrix in X transpose QX just manually.
So there is no Q matrix. I'm not doing LQR or DLQR. I'm not doing that.
You have to have some kind of, you're assuming a Lyapunov function. So how is the assuming process? What is the assuming process?
I guess this is something to do with the way we think about Lyapunov function. The traditional notion, as I said, is to think of V as a function of X, right, and not of controls. Here in this case, as long as, well, we have tools for LQR, right, and that's why we stick with LQR, and that, I think, constrains us to certain Lyapunov functions which are small region of attraction. But if we can reverse the logic and ask ourselves the question, given this Lyapunov function, what controller, nonlinear controller, will give us that region of attraction? I guess it's a different way of thinking. It's not, I mean, I'm happy to continue the talk afterwards.
Okay.
I can't hear. Yes, absolutely, absolutely. It'll very much depend on what Lyapunov function you pick. Absolutely.
Great. So it's control Lyapunov function, not a Lyapunov function. But in order to claim, to be able to claim that it's a control Lyapunov function, you have to come up with a control law, feedback control law, that derives Lyapunov function with negative rate. How do you claim there is one?
So yeah, so what I'm saying is, okay, so there's some difference between traditional control Lyapunov function, which is a continuous control law, versus this one, which is, in this case, when you think of walking, you're thinking of, it's not a trajectory tracking problem, but it's a set point control. You're trying to control something over a complete step, like foot placement, so that you're back to the nominal limit cycle. So given that, there's no control law per se in the traditional sense. It's not U equals f of x in the continuous sense, but it's u equals f of x, where u is control x state, in the sense that given that u and you stick to that u, you'll get back to, you'll reduce the Lyapunov function. So the control law is coming later on, where you're trying to do regression to fit it.
But once you use Poincare section, you just discretize the system. Like, then it becomes a discrete system. So things don't change, I guess, like today. Just discrete perspective, and same rules apply again. You have a discrete controller, doesn't
That's
change.
right, it's a discrete control. So you always assume there's a low-level controller which handles, for example, foot placement. All you can do is, every step is change your foot placement or change the push-off. You decide that foot placement, and there's a low-level control which takes care of it. That's the assumption.
Okay.
Is that, no? Does that answer your question?
Kind of. We can talk later.
There's another question sort of in the middle there. And then Noah?
Have you incorporated actuator constraints at all? I worry that if you're prescribing a basin, it might put undue stress on the actuators.
Yeah, so so of course when I found those control laws, I assumed there was no restrictions, but clearly if you go at a faster speed, so I was looking at 5 meters per second and a height of 1.3, but if you go faster, clearly you will not be able to find a control law because you will not be able to find any control actions because you're clearly violating actuator limits. So I have not considered limits.
Noah?
You're not proving this is layout.
I'm not.
You're numerically evaluating that you picked a law that makes the system converge numerically.
That's right.
Okay, so I think that's where some of the confusion was arising.
It's all data driven. There's no proof that it's.
I see.
And my fidelity depends on how much I can simulate and how much I can show numerically. That's absolutely right.
Just a clarification, not a criticism.
One over there, and then Art, and then I think we'll wrap it up. And move on to video.
So since this is a data-driven approach, obviously it depends on your ability to sample, right? So you've used a model where you can infinitely sample, but if you needed to use this on a real robot or like some environment where it's complex to model it, how would the sampling process work? And if you're constrained by sampling, then what happens if you're outside what data you sample?
Yeah, so I have not thought about how can you do it perhaps in experiments where you have a complex system or it's not a very well modeled system, then clearly what I've talked, I have to think over and fill in the dots. So I don't have a good answer to that question, how to tackle a non-model system. It's assuming that you have a model and the model is reasonably good.
My question is maybe just a question about vocabulary. I'm not sure if you have to call it Lyapunov function. So is what you're proposing similar or part of their differential inclusions where instead of projecting forward what's going to happen to a state, you're projecting forward what would happen to a set. And then that set can be ellipsoidal. And then, there are various techniques for predicting what's going to happen to an ellipsoidal set.
Well, I didn't know that before you said that, so I got to check for differential inclusion. So
Yeah,
that's probably
differential inclusions, or in this case, maybe difference inclusions.
Thanks.
Okay, sorry. Let's thank Pranav.